So we're going to talk, as I mentioned, on bridge superstructure and bridge deck applications. For background, you can go to the ACI 228.2R document, which is in the ACI Manual of Concrete Practice. I happen to be a member of this committee. But it is a report on non-destructive test methods for evaluation of concrete and structures. And you can see on the slide a whole range of test methods that are listed. So this is a good background with a lot of references that you can look at later. There's also a 228.1R document that is on non-destructive test methods for strength estimation in concrete. So some of the applications, certainly we all start off visually. Bridge inspections are often combined with non-destructive evaluation. I'll mention that the Federal Highway Administration and through their National Institute of Highways educational group teaches courses in many different areas of bridge engineering and inspection for engineers and technicians in the bridge industry. And even though I'm a registered PE and I've looked at a lot of bridges, there is now a class, a seminar, a 1 week long class. It's 2 weeks if you're not a registered PE on it's in person, but it's inspection in person for safety of bridges. So I've taken that, so I am a certified MBIS bridge inspector. But that's where all bridge inspections pretty much start, is visually, which is non-destructive, of course. And now there's more and more applications where DOTs are looking at drones, but we're not going to talk about drones today. But they're using them to inspect their bridges as well. So in concrete, in particular, impact echoes a test to look at concrete cracking, one-sided for corrosion damage, lamination, honeycomb thickness, and looking at voided versus grouted ducts. Spectral analysis of surface waves, something developed by Professor Ken Stokey when I was in graduate school. My office mate started research on this method. It allows you to look at variation of velocity into the concrete for cracking, crack depths, competency of the material, velocity and modulus, as well as void and honeycomb issues. We'll talk about ultrasonic pulse velocity and tomography to image internal flaws with two-sided access. The first two tests were one-sided. Ground penetrating radar is generally one-sided access for steel mapping and corrosion potential. Slab impulse response, we won't touch on today, or infrared tomography. We'll touch a little bit on galvanostatic pulse for rebar corrosion rates, and ultrasonic pulse echo for testing of steel for section corrosion loss and anchor bolt integrity. So the first topic, I gave this recently at an ACI spring convention, the American Concrete Institute. Virtually, everything's virtual so far. We're about to see conferences finally go back to being in person in the fall, as I guess you as students are probably going to be back in person if you weren't already this spring. But this talk was on using photogrammetry for detailed mapping of the concrete surface distress conditions. And we also use various NDA methods for these bridge girders. And it's 3D ground penetrating radar for detection and mapping of the embedded reinforcing. The post-tension ducts and steel plates, as you'll see, is fairly complicated bridge girders. Spectral analysis surface waves for the extent of cracking, perpendicular crack depths, the void, honeycomb, and velocity modulus. And impact echo scanning, where we're rolling kind of like radar, but testing every inch to look for cracking, corrosion, delamination, damage, honeycomb thickness, and in this particular project, in particular, voided versus grouted post-tensioning ducts. Finally, the data fusion overlay concept is to overlay the NDE results on the photogrammetric images to give you both a visual impression and the underlying internal concrete conditions from the various methods above. So if you've not seen photogrammetry, it's pretty straightforward. You'd like to take, you can do it even with a decent quality phone camera, but you would like to get angled photographs that are all put together in software. Can take a while to process it, but it will give you a nice detailed image. It almost has a quasi 3D effect. If you look at this, you can get a better sense of the depth of, in this case, a cracked drilled shaft foundation at transmission tower. You get a better sense of the severity of the cracking damage and the conditions on the surface. It's also used, the files are quite large. The files can be saved to monitor deformations over time and see how the surface degradation progresses over time. So it's a good baseline as well as a good image to overlay on. The resolution is so high ultimately that you can't even show it on a computer screen. So it can be zoomed into, of course, but the fine detail is there. So the method involves you get this raw photographic digital image, as I mentioned, with a decent phone camera or telephoto lens camera for larger structures. Get target features that occur in multiple photographs. You use the angle changes to turn it into a 3D structure of the object. It can actually be used in modeling to create a 3D structure if you were photographing something smaller. With various, like almost like some of these so-called 3D printing machines that would make a plastic model for you. You can project pixels from the photos onto the 3D structure, generate texture. We used a software called Agasoft Metashape. You want to have a very good Windows PC with a fast processor and GPU, because you will crunch away for 2 to 4 hours, depending on what you're using to process it. You don't have to be there the whole time. It is processing all this data, but the computer will be processing the data for you in the software. High resolution. You know, this is, I mentioned, you can see fine resolution of cracks and images. Gives you 100% coverage, but large data files. So there's several advantages. It's relatively low cost equipment. You can see this progression of deterioration over time. You get a detailed permanent record of defects marked during inspection, and you can view it with something as available as a Windows 10 3D viewer. You only get data on the objects in the line of sight, obvious limitation. And multiple angles and photographs are going to be required, so you do have to spend a little bit of time to get very good coverage and make sure it overlaps in your photographs. As you'll see, we established a grid which helped the software to process it. It could line everything up. So here is an example of the bridge girders. There's a top web of a girder that's coming into it and a bottom web. If you look in the middle, that's actually where there's a diaphragm, a concrete diaphragm, bracing across transversely this older bridge, stiffening it, but that is not shown in the image for obvious reasons. We couldn't take a picture that would show in the image, but that hole is where there's a concrete diaphragm that goes through. So here's the bottom web. It goes from a thickened end to a thinner web section, nominally 10 inches, and the web was 20 inches deep. So we did testing from both sides with various methods. You can see the 6-inch grid that's been established. And you can also see some of the marking that has been done in the past on this to highlight cracks and features. So one of the first things we did on the project was ground penetrating radar. This is 3D scanning, can be done by scanning in 2 directions for mapping out reinforcing and metal embedments. So we use high frequency antennas are typically used at least 1500 megahertz. The center photo shows 3D scanning on a guide. You can also lay out a grid. In the end result, by scanning in 2 directions, both vertically and horizontally typically, and you can see the grid here as well on the left, you get a 3D image and you can slice that at various depths in your data set. And that's showing the rebar. So it's almost like an X-ray, but it is safe to use. You don't have the radiation emission of an X-ray where you have to back up at least 150 feet and the public is exposed to radiation. So often see a lot of ground penetrating radar done for structural steel reinforcement and embedment mapping. There's an ASTM standard on radar that's listed. That one happens to apply to scanning of bridges for corrosion of decks. Now, the physical principle of GPR. You move it along a line and you have a distance wheel that's embedded in the unit and you record the data with typically 48 to 60 pulses per foot, not being uncommon, for structural applications. So it looks for changes in electrical properties of materials, and the metals are a very strong reflector because it's 100% reflector of an electromagnetic wave. So having said that, this is a schematic that you can see right here of an antenna shown with a transmitting antenna and a receiving antenna. You push that along, and below it is left to right is the plot going from 40 to 44 feet of the reflected radar signals. So having said that, you can see at the left, that is not as clear a signal. The signals are much clearer. The center of this hyperbolic reflection is the black spots. That's the top of the rebar. And you can get depth of cover by calibrating it for the velocities of the material. And you can get that from the shape of the hyperbolic fitting of these curves from single rebars, or if you know the thickness and see a good backside, you can do it that way as well. So having said that, why is this fuzzy? Well, the presence of de-icing salts and corrosion byproducts and moisture attenuates the signal. So one of the ways that people have used radar to estimate, it's not exactly damage mapping, but it's probability of damage in favorable conditions for corrosion and delaminations, it's a weaker signal, lower amplitude. So that can all be taken out of radar data. So here we are scanning. In this case, we weren't trying to estimate the corrosion. That's more typically done on bridge decks. We were trying to locate the metal embedments. This particular unit is a higher frequency, 2700 megahertz, that has a screen built in, very convenient to use. And you just roll it along the concrete surface. You can see the 6-inch grid. So we were able to scan, in this case, we wanted to scan every 3 inches horizontally and then every 3 inches vertically, using the 6-inch grid as the guidance. And you can also see some of the cracks and other things showing up in this photograph. All right, having said that, let's take a look at the data. So in the upper right is the unprocessed radar, so-called B scan, because you've got distance across the top or plotted along the bottom axis, and depth from the surface going into the member. So this shows tendons. In this case, we were scanning for tendons vertically that are showing up here as these features that are hyperbolas along the length. Then you do what's called migration to collapse the hyperbolic reflections from the rebar and tendon ducts to their locations. So that becomes the center points of the various tendon locations called out there, and the rebars being called out above it. So you've got both rebar with the tendons, which are really reflections from the post-tensioning ducts, because the tendons are grouted in steel on the inside, but we first see the metal post-tensioning ducts because that's the first reflector. So then there's another further processing that makes it even a little more clear, called a Hilbert transform, that again shows, in this case, the tendons and the rebars are being highlighted as pointed out in the scan. And this is all turned from a time reflection in billionths of a second to depth by the calibration. So we found both rebar and post-tension tendon ducts, which is important in the project to know where they were. Even though we had design drawings, it was quite old, and you never know how things are exactly built. So to do a little data fusion with depth slices for the post-tensioning ducts, the rebar, and the embedded plates, interestingly enough, there are embedded steel plates in these girders where they come together at this joint as well. So you can see here's a 4.1-inch depth slice for 2-directional gridding in the web of the girder, the thinner 10-inch section. So now we're able to track these features are showing where the ducts are, these stronger, brighter reflectors. The next thing that's shown on this is the thicker 20-inch section, and we did scan with radar from both sides because it can penetrate approximately 20 inches, but you get higher resolution if done from both sides. So in this side view, we've identified, and it's complex. These are some stirrups that are in there at angles. There's vertical bars and some bars coming back this way. Plus there are embedded metal plates that are all inside the ducts. And you can see these outlines are drawn to show the features and the interpretation. Here's some horizontal rebar. And we, because of all this other steel, we weren't exactly, you can sort of see the extension of the duct right here. You can see the extension of the duct is coinciding in this general area here. And then the anchorages are over here for the ducts. So on this side of it, the top web of the other girder coming together, this is showing, again, the stirrups, some vertical steel, and 2 steel plates here and here. And then it becomes clearer at this depth slice, 3.5 inches in, that's when you see the post-tensioning ducts. So this is being sliced in this case to be behind some of the front steel. You can still see some of the front steel in these reflections at this depth of slice. And the reflection amplitude is shown on the right. And I should mention, I think that if you have any questions, to please ask them. I'll just have Cheryl monitor the chat. And I'm not sure if you have the opportunity to do it verbally or not, but certainly we will address any questions either at the end of the talk or if it's real urgent as we're going through this. So far, no questions in the chat. Okay. So the next technique we used is very good for evaluating distributed cracking in concrete, as well as depths of perpendicular cracks. And we've used it in special applications on bridge decks as well, that you'll hear in a bit. But this is called spectral analysis of surface waves. And you impact the concrete with two receivers in a line. We use a bar that we make in Olson Instruments and connects to a data PC that we make as well to take the data, and does a bunch of different ultrasonic, sonic tests. But you measure the wave propagation of a surface wave between the two receivers. And you're still in school, so you probably remember from freshman physics that surface wave velocity is equal to the frequency times the wavelength. So what does this do for us? We get a measurement of the velocity profile versus depth into the structure. So this can be related to the strength of concrete and the condition of the concrete, cracking damage, depths of perpendicular cracks versus depth, which is related to approximately the wavelength. And again, this is discussed in the ACI 228.2R-13 document. So here's some platforms just to show the equipment a little better. We also have more portable, ruggedized, handheld unit with a touch screen and a compact flash, but you get the most processing, of course, if you're running it on a Windows field PC. And this shows the equipment, a close-up of the SASW bar. It can be extended out to 80 centimeters with the extension, and spacings going from 6 centimeters to 80 centimeters at different points of the two displacement transducers. You impact with a simple hammer or even higher frequency, smaller impact, in line along the length, and you get the necessary data. So what's the data look like? These are time voltage plots. The big spike of the energy, this is time and this is a voltage, or it can be calibrated to be the response of your transducer. But the big spike is the surface wave energy, because when you hit the concrete, about 2/3 of the energy you generate is surface waves. 26% is shear wave energy, and 7% is a literally compression wave, the impact echo type energy that we use compression waves for, or ultrasonic pulse velocity, as we'll talk a bit too. So you can see the bottom one, it's slightly later in time when the big surface wave pulse goes past. You window in on that to produce a phase plot. And the phase plot is shown here. What you've got is coherence in the top for a frequency of up to 12,000 hertz on this thick piece of concrete. It was about 5 feet thick. And in the bottom is the phase plot. This is called wrap phase because it shows how much delayed, in a simple sense, is the response of the second receiver in time, but in this case, analyzed better in frequency, with respect to the wave going by the first receiver. And then what that means is this is zero phase. You can basically get useful data from about minus 120 degrees and higher. That's 3 times the spacing or wavelengths of your receiver spacing. And so what you do is you say, okay, it's very uniform. This is very uniform concrete. This is one wavelength. It's slightly offset on the arrow, but it's crossing there is 2,628 hertz at minus 360 degrees. So that's one wavelength. 720 degrees lagging would be 2 wavelengths. This is spaced 2.62 feet apart. So at one wavelength, the math is simple. Frequency times wavelength equals 2.62 times the frequency of crossing equals 6,900 feet per second. And this would be very similar, but the frequency is higher, but the wavelength is half. And so you get this data that becomes a dispersion curve, which is surface wave velocity versus wavelength. So what you've got here now is, again, good coherence when the signal's above 0.9. Even with phase, it's not as critical that it be above 0.9 as in some other tests, but it's still pretty good data for the 12,000 hertz range of the measurement. That's a very uniform concrete. It was high quality, strong concrete, 6,900 feet per second. Didn't vary much at all. So here we're doing our testing. Again, back to the girders. We're doing it horizontally. You can see the impact's going to be applied in line on the left, spread out, measuring the responses at the first receiver closest to the impact and the second receiver further away. And this was 1.31 feet apart with a small light ball peen hammer hitting with the ball end, just to get a higher frequency energy. So what do we get? The velocity versus wavelength plots or dispersion curves are shown here. So on the left, this backside of this sound 7.5 inch thick web section has a drop in surface wave velocity at from 7,000 feet per second, from wavelengths of 4 to 8 inches, to 5,500 feet per second. This is the backside of the section because it goes off in air and doesn't mean anything. So this test was across a crack on the girder, and it indicated crack depth on a thicker section at the ends of 20 inches from the surface to approximately 7 to 8 inches deep. So this goes from 0 to beyond the thickness at 20 inches, but it's showing that it dropped in velocity right in here, and then it picked up again. So the velocity drop was from the surface, and it picked up, indicating about a 7 to 8 inch crack. And then you're beyond the thickness in this location. So having said that, one of the other problems of the project, because it was older, is there was concerns about voided versus grouted ducts. If it's not well grouted, that can lead to post-tension corrosion. This was first discovered in the United States in the late 80s by the Florida Department of Transportation, and Teddy Thoreau was involved in this project with Parsons Brinckerhoff at that time, and it's now WSP, at the Sunshine Skyway Bridge in Tampa, Florida. You might have thought the corrosion was in the girders, which were also post-tension. This is a cable-stayed bridge. And they were actually, though, in these large piers, which were constructed because of the risk of ship impact to have some protection, but they had trouble grouting them because they had U-shaped ducts that went all the way down into the pier foundation, pier caps, if you will, and then curled back up. Well, they had real grouting problems, which led to a lot of void because of the saltwater environment of the Gulf of Mexico. So what you can do to check for voided versus grouted ducts, and I think you're going to hear our train going by, is the impact echo test. And what's shown here is a handheld unit where there's a solenoid impactor and a receiver that picks up the resonant echoes. You can see an echo at a shallower depth and a higher frequency of echo. It's a resonance test, as we'll talk about, that would correspond to a flaw, such as a voided duct, or a planar flaw, such as cracking would be a very distinct echo in a horizontal plane. So full thickness echo, of course, is part of it too. That would be sound concrete. We make devices as Olson Instruments from simple gauges that can run out of a Windows tablet into the audio port with a built-in similar battery-powered impactor and displacement transducer. And what you saw on screen perhaps is the 5.2-inch thickness echo of resonance, and that's the time domain signal of which a FFT is done, fast Fourier transform, to get the frequency content. Responsive displacement transducer has a resonant echo that corresponds to the thickness, in this case, 5.2 inches. So what are we doing? We impact it. You could see the full thickness. You could see an echo from a crack. You get the responsive time domain. You process it with the FFT per ASTM standard given here. And depth's equal to a shape factor, which is 0.96 for a slab shape. And it's a lower factor for beams and columns, depending on their shape, depth, to their aspect ratio of width to depth. And you get multiple resonances if you have a column shape. But then finally, on a flat slab, you have a single resonance of echo if it's the solid concrete in the thickness, and you calculate it as this factored impact echo velocity divided by twice the frequency of the resonant echo. So this shows an impact echo scanner that years ago I came up with that idea and got a US patent on. And it was just an idea after doing endless point-by-point testing. I said, there's got to be a faster way to do some of this testing. So I was inspired by tedious testing to come up with the scanner, similar to radar. So you roll an impact. This has sensors embedded in this spring-loaded wheel that are an inch apart. There's the solenoid impactor. We have a normal size and a little heavier one to see deeper, lower frequency energy, higher energy. And you can select one or the other, and every inch as you roll this with this spring-loaded impactor, you have to stay in contact with concrete, you get a test result. So we got some funding to adapt this idea to find voided versus grouted ducts from the National Cooperative Highway Research Program, their Innovations Deserving Exploratory Analysis contract. And we're very lucky and fortunate to get that. It's not easy to win these at all, a lot of competition. And so we grouted in these. We were donated the girder because we tested it with radar, and unfortunately for the precast yard, they had put the ducts in the wrong position. So they said, well, you can use your girder, our girder, for testing because we can't use it for the project. So they gave us a girder. The wall thickness was 10 inches. we grouted in the styrofoam void, had a repair contractor grout ducts the first 20 feet of the girder and created known voids. This was research. So as we rolled across them, what we saw was a fully grouted duct, had this echo resonant frequency peak of the energy bouncing back and forth, resonating at 6,445 hertz, predicting 11.17 inches when it was fully grouted. Only 3-day-old grout, so this was pretty soft grout still, but hardened. The empty duct, though, resonated at an even lower frequency of 5,274 hertz, where that styrofoam void was in place, and that produced an almost 14-inch thick echo. You can see the shift downward in the resonance. So this 22% apparent thickness increase in the echo was due to the void. Think of it this way, that as you may recall, when you have a mass in a spring, that as you get lower stiffness, the resonant frequency is lower. Well, this is a less stiff section of echoing in resonance. That's why the resonant frequency shifts downward. Honeycomb void can have a similar effect to a void in a duct because it's less stiff because of the resonance. Okay, so what do we see? In a side view of the data, where the scales on the right of the green is the normal thickness, and getting away where it's grouted, you can see 4 ducts are stacked together. The top duct had these voids created that you can see. And you also see in the color scale how it got thicker in those zones where the void existed. So it correlated well. You can take all of the data and kind of skew it in a 3D view where this is the thickness of the echo from 9 to 14 inches. This is the top duct we were just looking at, the second, the third, and the fourth, which is supposed to be well grouted. At the ends, we had trouble getting good grouting because that's where the grout emerged from inside of the ducts. But this is the 20-foot length. This is the scan height up the wall with the scanner. So here we are scanning on the girders again. We did vertical scans because we were most interested in this case in the post-tension ducts. So we're cutting right across them as they are in the horizontal plane. So as we push this up, every inch, this is impacting the concrete. It's important to keep it well coupled. We're recording the data. We did it on a 6-inch grid throughout the ends of the girders and the web sections. So what do we get? Grouted versus voided ducts were best done in the webs because they're thinner, and that's where we wanted to check it. This is the third line out of 6 lines in a row. You can see it's coming right in around 7 inches, 7.5 inches, because that's the thickness we expected here. But the poor or void duct grouting conditions showed an increase in echo thickness from 8 to 9 inches to 12 inches in this zone here on the right. So this is an area indicating a likely voided duct because we know from the radar where the ducts are as well. So as we look at the next, this is how it plotted in a data fusion sense of overlaying it on the images. You can see in the webs where the radar found the duct locations of the post-tensioning, and you can see in the color scale on the right showing internal laminations, and this is an apparent thickness plot that's showing that scale as well. And as you look here, it's questionable or poor grout with a solid delamination, 2 possibilities. But if you're right over the duct, you're pretty sure that that's an area of concern for grouting, as these results are showing. And then as you look here, sound concrete versus questionable or poor grout, not quite as severe a change. And those are all plotted, as you can see by the diamond colors. And the impact echo area also showed some areas of questionable or poor grout when these colors versus delamination in these colors. And the surface wave showed cracked tip depths ranging from less than 2 inches to more than 10 inches. And these are the dots that will also be overlaid and are overlaid in the plot, where we're showing some interesting results that way. So we're starting to fuse everything together. The final one shows it all, where you've got data fusion and the impact echo scanning, the surface waves, and GPR duct grouting, GPR locations of the ducts, in terms of grouting and locations for the girder end walls. So again, the scales are explained there. You're seeing surface conditions as well as the underlying non-destructive evaluation results, and of course, the locations of the ducts. So shifting gears from that, Here's just a summary. Photogrammetry gave a detailed imaging of the surface. The 3D radar can image the complex, very complex in this case, reinforcement, post-tensioning duct, and metal steel plate embedment conditions. Surface wave gave data on the depth of the cracks and the integrity of the concrete, as well as providing one-sided velocity measurements. Stronger, faster velocities are stronger concrete, higher modulus concrete. Impact echo scanning found grouted versus voided post-tensioning ducts, as well as delamination and cracking damage in the concrete. And we integrated it all for the project with data fusion of the various results to help provide a more clear, easier structural assessment of existing conditions and areas in need of repair. Okay, another technique that we've used on bridges, in this case, it's a big bridge column. That's part of a big bridge sign, actually, on an interstate. So I shouldn't have called it a bridge. It's a column sign, a very large digital sign. But we're sending ultrasound through on a 1-foot grid because nobody consolidated the concrete. They just dumped it, and they ended up with void and honeycomb. And chipping into that surface found the void and honeycomb. So now the state DOT wanted to see if they could save the column or not. So we did ultrasound, sending sound waves north to south and east to west with this small transducer. It's the ultrasonic pulse velocity transducer. And a similar one's on the back side. It receives the signal, and it shows a good arrival at 372 millionths of a second. This is time and voltage. If you do the math, velocity equals distance divided by time, or excuse me, it is distance divided by travel time, and you come up with a velocity of 13,500 feet per second for this 5-foot thick column. And a test example from right next to concrete on honeycomb showed virtually no signal, very delayed, very weak signal. And it came in at 552 microseconds right here, a little bit of energy. That corresponded to a velocity of 9,100 feet per second, much slower. So you do these measurements. In this case, we just went north to south and east to west. If you can do angle tests, you get even better imaging. In a simple sense, by doing tomography, you're assigning velocities to the pixels in the software to best match your data. And you can do it with straight ray testing analyses or bending ray, which allows the wave energy to find its fastest path. So what do we get? Here's an example. This is a cross section in that area of void. On the north side is where you saw that visible honeycomb and void. And we're testing straight through north to south and straight through east to west on a fairly large grid of 1 foot. But the goal was simply to find out if they could save the columns or not. You can get much better resolution if you go tighter, but you can see only about a quarter of this column had good velocities above 12,000 feet per second. That's generally considered good quality concrete. 10 to 12 is questionable, and below 10 is poor to very poor. And these are in thousands of feet per second in the color scale. So green is good. A lot of people like the traffic light approach. Green is good, yellow is questionable, and red is bad. You have to stop. It's simple. So this is another project on a bridge pier. In this case, it was heavily reinforced. It did a good job of concrete placement, but it was such heavy reinforcing that it was difficult to get it fully consolidated. They saw some surface honeycomb in the massive piers back here with all the reinforcement. And so with access from the lift, we did testing around the corners and in these areas of honeycomb, because you have to have crossing ray paths. You can test straight through if you can go all the way through. We couldn't. You can test diagonally at angles, different angles to get crossing ray paths. That's very important. And that's what we did. We had a grid on the front face, and there was a similar grid around the side to define the depths of this near visible void and honeycomb, mostly honeycomb. So we sliced the data, and here's a velocity scale. Again, 12,000 feet per second and higher is good. Going down into the blues is poor quality and slower. You can see at various depths on this foot grid of where the voids and honeycomb, the poor quality, slow velocity concrete was, which was honeycomb, that they could now, this one was fine, but they could now decide where to drill to inject it, to fill it with epoxy and repair the internal strength of the concrete. I should point out that research has been done by the Portland Cement Association that showed for just a 5% loss of concrete density. So you drop from 150 pounds per cubic foot to 142.5. That corresponds to a 25 to 30% loss of compressive strength or flexural strength or tensile strength. So you really do need well normally consolidated concrete to achieve your strength. So not having it can be a severe penalty. If you lose 10% of density, it's a 50 to 60% loss of strength. So you definitely want well-consolidated concrete. So a picture is worth 1,000 words. Giving people an image, we've done this on dams, on underwater testing of drilled shaft foundations with process like logging, on geotomography in the soil and rock. But tomography is used for a variety of things, similar to CAT scan that everybody's heard of, except that's amplitude of radiation tomography. And now we're talking about speed of the stress waves, of the sound wave tomography, for a velocity tomogram in this case. You do take more testing, more detailed analysis to get an image. So let's see how I'm doing on time. I think I'm okay. I've got a little bit more time. Very quickly, this is not uncommon, it's commonly done, but I thought you should see that you can do ultrasonic testing for corrosion of metals. It puts out a high frequency pulse, you get a time domain echo, and if you saw a thinner corroded section, something inside this can would be chemically attacking it, and that's an example of corrosion. It's thinner than expected versus tests nearby that's showing corrosion. Here's an example of applying it to steel girders. You can use calipers and shine it up and measure it, but ultrasound has some advantages. And you still have to get good coupling, but you can see how much was lost. This one, with all of the icing salts used in the northern United States in Indiana, had 60% loss of sections because the problem was at the joints, the water came through, the icing salts ran down the girders, and you even got corrosion out at mid-span on the bottom flanges of the girders, as well as in the connections. So here's another thing that's important to check, can be in bridges as well as anchoring other towers and columns, is anchor bolts, and are they broken or not? And we did find some anchor bolts are broken. This was a 6-inch echo in the pulse echo result. With testing on top of these bolts, it should have been 24-inch long anchor bolt. And this can go out to over 120 inches. We've tested some anchor bolts, this particular system. So now the last thing we're going to talk about today is bridge deck condition assessment. Common problem, more than half of the maintenance money in the United States is spent on repair and replacement of bridge decks. So you can do it by visual assessment and sounding. Typical chain dragging that people have used or hammer sounding for years. There's been studies that have shown that's subject to the accuracy of your ear and experience. And you can only hear about 3 inches deep into the concrete. Impact echo scanning, probably the single best method for delamination mapping on bare and epoxy coated concrete decks. We use surface waves along with impact echo, but it's harder to get impact echo to resonate on asphalt because it's typically warmer. If it's very cold, it'll work. But it will actually map out the severe delaminations, top and bottom, on an asphalt overlay deck, as you'll see. Ground penetrating radar scanning is used to estimate the areas of damage. It's about damage potential, get you the top steel depth. It can't really check below that because of too much energy reflected at the top steel. But of course, if it's the icing salts and not sea salts, when it can come up under the bottom of the deck, it's a lot also and cause corrosion damage on the bottom of the bridge deck. It will work well for that. Infrared thermal imaging sees top steel delaminations. We've used that as well. Again, within the first few inches of concrete. We'll talk a little bit about galvanoscopic pulse today for corrosion. And then on the end, the last thing we'll get to hopefully is how you integrate all this with coring and lab tests and predicting remaining service life. So here's our sonic surface scanner. This came out of an NCHRP idea grant as well. We took the basic idea you saw in the handheld scanner and upsized it to have these rolling impact sensor wheels where there's sensors, displacement transducers, and impactors every 6 inches, hitting left and right for impact echo testing as you slowly roll it. There's a close-up view of that. You can see the solenoid impactors and the brass transducers. We've recently added GPS to it, which makes it much easier to track it and very precise within a few centimeters with the base station and the rover GPS on the unit. So here's a close-up of that. There's the transducers that put all that wheel weight to couple well to the rough concrete and a fairly sharp impact from the solenoid as it rolls around its time to hit the concrete when this sensor is down. This problem here was brand new deck, shouldn't have been corroded at all, but they were worried they had void, internal void, because they concrete set up too fast. It was rough on the surface and had some plastic drying shrinkage cracks. So we ended up scanning it. We saw features in the scanning to prove the consolidation in this case, but where it was thicker because of good coupling to the underlying girders and piers across it, we saw thicker echoes. At that time, this was earlier in our research, we hadn't yet developed the cart. We were simply pulling the system on a wagon. We did a 1 foot grid going across the deck with tests on each alternating wheel. It was very rough concrete, as you can see, but it coupled well. We got very good quality data. Here's 100 feet of data. The 12-inch thick approach slab, this is thickness on the bottom. That's nominally 12 inches. And it drops down into the nominal 8-inch thickness of the bridge deck. We didn't see any huge increases in thickness that would have corresponded to internal void and honeycomb. But here's the signal. There's the resonant frequency peak saying, oh, that's 8 inches thick. And that's the time domain signal from which this FFT produced it at this location. So very good data. This is the plot of the results. It's a color scale again, showing that we got mostly the expected deck thickness, but when we were over the underlying beams and diaphragms, it looked thicker, and the approach slabs were 12 inches thick. They were the thickest, but we didn't find anything indicative of internal void or honeycomb. This is a research study by Rutgers University that was done in SHARP 2, and they invited groups to demonstrate technology on it. SHARP 2 funding from the FHWA, and we were one of the groups that volunteered to demonstrate technology. And they had a small but very corroded deck area of this bridge over I-66 in Haymarket, Virginia. So this just shows a sound thickness resonant echo for sound concrete in a deck. You can get echoes that come from an internal crack, but you also can still see, that's the crack echo at a higher frequency. You can still see a thickness echo, might be shifted down a little. You can get deeper crack echoes, and this is showing a deeper crack echo in this case. And you can get the top delamination, which doesn't show up as an echo, but it's a flexural resonance because that piece of concrete, you can audibly hear that hollow drummy sound, like you chain dragged it or hit it with a hammer. That shows up as a flexural resonance because that piece of concrete is literally flexing. So what we get, this shows the sonic, what we call our sonic surface scanner now with impact echo scanning, yellow and red being the delaminations, yellow showing some cracking damage still, versus the chain dragging by the Rutgers University students. You can see it agreed very well. We had more resolution, not surprisingly, with the impact echo scanning. The Rutgers students did not hear this delamination at this end. So this shows all the data, including the bottom light colored blue that is showing underside corrosion of the steel. The bottom steel is corroding as well. Where you don't have a top delamination, you're checking the concrete integrity all the way to the bottom, and we were seeing some areas of corrosion on the bottom, which typically exist. The software turns that all into areas of percentage of top delaminations, 14%, incipient, meaning not so severe delaminations, 13%, and about 6% was the bottom delaminations. Sound concrete was still 67%. Of course, that's not very good. I think the Virginia DOT, it varies, of course, as to when they decide a threshold that they should repair or replace a deck, but most DOTs operate someplace in, by the time they get to 20%, they're often repairing or replacing it. Virginia might even be a little stricter than that to start to try and address that earlier. So we also did some radar work on it. I mentioned you can scan with this particular system 2 directions simultaneously on a grid because it has 2 sets of antennas, 2 pairs or bipolar testing, front to back and left to right, which can get you a faster image of internal conditions. This just shows the advantage of scanning 2 directions. Here in this left to right channels, it was picking up the shallow rebar. But the deeper post-tensioning ducts were only seen in the front to back channels because of the way they cut across the steel. So orientation antennas mean something. This allows you with one scan to find both ducts at different angles than the reinforcement. So here's a comparison of the sonic surface scanner, the S-Cube with impact echo. At the top, to ground penetrating radar that we did. This was analyzed based on attenuation of signal and normalizing for depth of rebar. And the chain dragging at the bottom. This GPR results were calibrated against the impact echo because you have to decide thresholds of corrosion in rating this. Areas which are showing more attenuation of your GPR electromagnetic wave symbols. But you can see reasonable correlation of all the methods. The impact echo scanning is the most accurate. And it's really sensitive to the true damage in terms of cracking damage as opposed to the damage potential like radar. Plus it sees full depth if there's not a top delamination. So this compares again when I mentioned they did some confirmation coring, this is in the upper right, the area where the chain dragging did not hear anything hollow. Well, there was a crack, all right, which in fact Echo found, but it was 3.5 inches deep. And there's the steel and the horizontal crack as the steel expands approximately 6 times in volume as it rusts, causes tensile stresses and connects across the top of the deck in a horizontal crack called a delamination. And this one, everybody heard and found it. It was a core. We heard it. We found it in impact echo testing. The students heard it in chain dragging at 2.5 inches. So we kind of concluded around 3 inches is probably as deep as you can hope to audibly hear with chain dragging. So this just shows a demonstration of technology for asphalt pavements. It was extended to that, doing both impact echo and surface waves. And what we're doing now is an impact echo test on the left, or excuse me, on the left wheel here. And we line up the sensors so we look with a very close spacing of 6 inches between the wheel, not a foot down. That gives us a surface wave result. And so we're doing this testing at Auburn University at their National Center for Asphalt Technology, because there are problems with new pavement construction of not getting a good bonding of the lifts of the pavements. They call that delamination of the pavement. If the tack coat is not properly prepared, if it's contaminated, if it doesn't bond, the pavement is much weaker. So we helped and got some funding from Auburn and their NCAT Center from this SHARP 2 project, R06D, to try impact echo and surface wave to find these delaminated asphalt pavements that they built. This just shows a back view of the sensor wheels. You do line them up for the surface wave scanning. And we found that surface wave velocity in a good section with no debonding was nominally 5,000 to 5,500 feet per second at wavelengths from 0.2 of a foot to 0.8 of a foot. Well, they put in a thin paper delamination. They also used dust, but the velocity dropped from 5,300 feet per second at a wavelength of 0.43 feet or 5 inches to 4,300. That was the depth at which the debonded asphalt was created. And we did all this initial blind testing. We did not know where the defects were. Ultimately, we were told that in this process, but it found it without knowing where these built-in defects in the pavement sections were. So it can find, it did work the best compared to radar. Radar works well if there's say water in the debonding, but if it's just an air gap, it's not so sensitive to a very thin air gap for debonding of asphalt. This led us to demonstrating that maybe we could use surface waves along with impact echo on asphalt overlaid concrete decks for the Colorado DOT. And that's what we did. A variety of technologies you can try and do asphalt overlay deck assessment with, but infrared is not going to work so well because it's black and you're hard to see anything in concrete. Impact echo scanning, if it's warmer, it just absorbs the energy. It doesn't really resonate. Radar can be complicated by de-icing salts and moisture, and it's again more of a damage potential map than it is a damage map. And surface waves did find delamination of asphalt pavement lifts, as you just learned. So here we are, pulling the wagon with the wheels, now lined up sensors, impacting as we go along. On this asphalt overlay deck, this was a repair project on a couple decks for the Colorado DOT. The data looks like this. Here's your surface wave data windowed. This shows the phase plots, and this produced a sound result. This was bonded asphalt on sound concrete around 5,300 feet per second or so, the wavelengths approaching a foot. This showed sound concrete with asphalt debonding. Right at 3.5 inches, we saw a delay in phase that corresponded to a drop in velocity from 5,500 feet per second at this wavelength of 3.5 inches, nominally 0.35 feet. It dropped in velocity. So that was the debonded asphalt. This result was deeper. This delay in phase resulted in drop in velocity at 5.1 inches, which was the depth of the top steel. So this was showing bonded asphalt, but a corrosion-induced delamination in the concrete top steel 5 inches deep from the surface. This showed two phenomena. First, a delay right here at higher frequencies in the phase plot that corresponded to drop in velocity from 5,300 to 4,300 feet per second, 3 inches deep. And at 7 inches deep, the bottom steel, it dropped in velocity again. This is the delay right here. So we processed all this data and said, okay, this is where we told the Colorado DOT it looked to be delaminated. And they said, fine, we're going to scrape out the asphalt and blast it with hydro demolition, which means high pressure water that'll remove any loose concrete and clean up the steel. And sure enough, what we predicted showed up and was outlined in these photographs here at 60 feet. So we did this initially blind also, and then they shared this photograph with us afterward. So we were predicting this shape of problems, and you can see where the steel is exposed, indicating it was delaminated concrete, corroded, and up here as well in the upper part of this photograph. So it worked, and we've gone on to test other decks with this. This shows scanning for detection of debonding on an overlaid white top deck. This was 4 inches of concrete in Northeast Texas. The Texas DOT they were concerned about debonding. We found a variety of conditions ranging from sound concrete in gray to debonding conditions in red to shallow delamination with low frequency flexural responses, all plotted out in these sections. So again, they could address repairs, maybe perhaps inject epoxy or something else to rebond it in this case. So the impact echo scanning is shown to have the most high resolution top delaminations. It'll also see to the bottom. The GPR method can't see the bottom delaminations nor infrared. It's not quite as precise. It can definitely be done at high speed surveys, as we're doing as well on asphalt overlay decks, when you are not as worried about exact precision, but want to get a pretty good sense of damage. And surface waves can find delaminations of overlaid asphalt bridge decks. And we also showed it for the concrete deck. So the galvanostatic pulse method for rebar corrosion, you have to connect to the steel. And basically this is exposed steel. It's easy to connect here. It had a failure right at the joint. And then you wet the surface and you test on a grid. It puts out a voltage that generates, in a simple sense, projects a current at the steel and the concrete. And it's polarized, and the decay of this polarizing current is what you use to evaluate the corrosion potential. And that shows half cell potential, which is part of the measurement of the galvopulse. And where it's very negative, it's much more likely to be corroding, minus 0.34 volts or greater. So right along that joint where all the de-icing salts, it was corroding. The concrete resistance was lowest because of the salt contamination of concrete, lower concrete resistance right at the joint. And the corrosion rates were highest at the joint. It's an approximate estimation of corrosion rate, but it gives you a sense of how fast it's corroding from this polarization decay. So the final thing, pushing on, if you take all this information on a project, you look at the chloride conditions. What's the depth of penetration of the icing salts? Because that leads to breaking down the natural passive protection of which is very alkaline in the concrete originally, to become acidic and start corroding the steel. Phenolphthalein can be done because carbon dioxide in the atmosphere will also cause corrosion of the steel over the long term as the carbon dioxide penetrates the depth of the steel. So we check for that on cores. You do compressive strength testing, unit weights, pulse velocity. You can do photography if there are concerns to check for cracking causes, degree of hydration, air void spacing, water cement ratios, size of air voids, alkali aggregate and alkali silica reactions, which are expansive reactions that can damage the concrete and expand with cracking, much like freeze thaw damage cracking, fire damage, etc. Can all be done. So here is just taking cores for pulse velocity and strength. These are the transducers. Faster concrete, if you calibrate for ACI 228.1, you can predict concrete strength, and we've done this, but you do need to get a calibration destructively. Otherwise, faster is stronger, but you don't know exactly the strength. So this shows chloride testing. You can do it a variety of ways. One way is with a fast testing in the lab, where you can drill small holes, get dust cuttings, and plot up the concentration of chlorides in percent, in this case, percent of cement by weight, or it could be percent of concrete by weight. And when it's higher and above a threshold, you have a likelihood of corrosion if your steel is at the same depth where it's above the threshold for corrosion. So sharp research, they typically say around 1.2 pounds of chloride ions per cubic yard of concrete will start to, at the depth of steel, will cause it to start rusting, breaks down that passive protection. Different conditions have different thresholds, wet or dry concrete. You apply fixed second law of diffusion as one basic approach to predicting the remaining service life. So you take your data, you fit this, and you determine really the surface chloride concentrations, and you get the diffusion coefficient. This all leads you to predict how the chlorides will advance over time. So you're fitting this chloride content versus depth line. You apply this to predict the remaining service life, knowing the depth of steel. And this just shows service life predictions from 50 to 200 years remaining, depending on the percent threshold of chlorides and the depth of the steel. Carbonation depths, you spray it with an indicator, and when it's clear, that's the depth of carbonation, and that's what that's showing here when it stays purple. So this is normally around 1/2 inch. And 7/8 of an inch, I should have said, clear areas. And finally, the service life prediction for carbonation is done this way with the bridge age and concrete cover depth. Based on knowing the age of the bridge and the carbonation depth, you can figure out the remaining service life as well. So I want to say thank you very much for listening to me today. I took most of the time, I'm afraid, but I'd be happy to answer any questions that you might have.
Larry, can you see the questions in the chat room, or shall I read them to you?
I will look. Yes, I can.
Okay.
How deep can the impact echo check for voids? Quite deep. It has to get to be a larger void, but the test itself can go out with normal testing about 2 meters, 6 feet or more. But it's most sense, then the size of the void has to be about at least 1/2 that depth. If it's distributed honeycomb, though, you will see a thickness echo that increases as long as it's substantial honeycomb. So, but there is that. Can you measure dead laminations on epoxy deck overlays? Yes, we have done that on a number of projects where it was overlaid with epoxy. And because it's hard, it works fine. So I do appreciate the questions, and I want to thank all the students for attending today, for Cheryl on behalf of the Try to Lead program and the FHWA for inviting me to be here. And certainly want to acknowledge Professor Kim at the University of Colorado at Denver. Jimmy Kim was the one who first introduced me to Cheryl and to your program. So thank you all.
Thank you so much, Larry, for presenting today. And again, this has been recorded and will be online. I do think that we have another question. Okay, this is from Dr. Kim. Thank you for sharing, and thank you for sharing state-of-the-art NDT technologies. I was curious about the accuracy of IES. When is the best time to employ IES?
Okay, and I think, as I understand it, we are seeing some groups actually interested to do impact echo scanning as quality assurance, particularly in early stages, for building new post-tension bridges. It's commonly done that way in China. We've sold a lot of our systems to China. They're building so many post-tension bridges. They are doing, and I've personally been in China and demonstrated. So they are doing that in particular check. In the United States, it tends to be the case history I showed from the United States was one where they knew they had a problem with the grouting on a new bridge. So we checked it then. Other people do it later because it wasn't done when they first built the bridge, and they want to identify areas in need of repair that might be corroding. So I know I gave kind of a broad answer, but I think that covers the ideal application would be when it's new, to check that, see that you've got it well grouted in the first place, and you can require the contractor to fix any problems. But if you haven't done that and you're worried about corrosion, then it's done later as the bridge ages and shows some corrosion damage.